So part 5. Students will apply the law of conservation of momentum to one-dimensional collisions and explosions. So let's think about these collisions. Let's say we have billiard balls, the classic example, because they tend to just bounce off each other. And they also have this nice feature that we typically start with a cue ball, and the cue ball is in motion, the ball it hits is not. We'll call this the before picture. And after the collision, the ball the cue ball hit is now in motion. The cue ball itself is usually going, but not as quickly. So we can use knowledge of the speed of the cue ball before and after, as well as either the velocity or mass of the other ball, to figure out the missing information. So we could say, we're giving you the masses of the cue balls, we're giving you the initial speed of that cue ball, and the initial speed of ball 2 is 0. And then after the collision, we still have the same mass. We now know the final speed or velocity of the cue ball. And then you could figure out the final momentum of the second ball. And if you are given the mass of that second ball, you can continue on to find its velocity. And the way we do that is by knowing that momentum is conserved. So this capital sigma is the sum of all initial momenta is equal to the sum of all final momenta. All the momentum that goes in is equal to all the momentum that comes out. We can deal with more complicated systems where both objects were in motion before the collision, or we can even deal with explosions. So we had one object at rest beforehand, and then two smaller objects not at rest afterwards. These are all common situations which would be good to review before we hit that first unit in Physics 30, where we take this one-dimensional concept and expand it into 2 dimensions.